This week we will move to a new topic, artificial neural network, or ANN, or here we call it artificial NN. It's the same thing. Most of you know deep learning. This is actually, if you want to understand it, we can understand it as shallow learning. Basically, we are talking about artificial neural networks with 3 layers or less than 3 layers. And when we are talking about deep learning, we are talking about neural networks with more than 3 layers. For this one, I hate talking too much about equations, math. However, in order to get an accurate understanding of artificial neural networks or the later deep learning, we will need to take a look at what's going on, especially in the key process called backpropagation. That's how to do the training for ANNs. In previous lectures, you guys can think about it, what we did. For the linear models, what we did? We got an analytical solution, right? So no equations are needed, just solve it. And then when we go to decision trees, what about the training process? Is there any iterative process? No, right? What we did is that we just split the data set into small subsets, do it step by step, and in that process, we will grow a tree gradually, right? And then we start talking about SVM. SVM, that's the first time we look into optimization, right? In that process, we need to put together the sub-object function or the loss function. And also, we need to figure out the constraints. And with those 2 things, we said that many conventional optimization packages in Python, they can be used to solve a optimization problem like that. So we don't need to worry about the solver. We just need to worry about how to establish the objective equation function and the constraints based on the SVM algorithm. That's what we need to worry about. And in this one, ANN, you will find that we will do it in a way that is similar to what we had for SVM, but slightly more complicated. Now, in order to create the objective or loss function, we will see that now it's not that straightforward. It's not like you put things together to get one equation. No, now it's more complicated. Now we need to do things forward, get a prediction first, get the difference, then you base the difference, get the loss function, then go backward. And when we go backwards, we need to see how we can update the different ways. Because for ANNs, now we have much more model parameters. In previous models, algorithms, you can see that we usually have 1, 2, 3 parameters, right? Now for a shallow ANNs, we can have much more. We have talked about 10, 20, 30, or even more. And when we go to deep neural networks, we're talking about millions or even billions these days for large language models. So for this one, we have, again, we need to, even it's not fun to play with the equations. In some cases, it happens in that way. However, it's needed so that we can all get a decent understanding of this. And later on, when we are talking about deep learning, you have the basic knowledge. Even at that time, I would not go through the deductions in detail, but you guys need to, based on what we learned today, you will be able to figure out, what we're kind of doing now. And for this lecture, for artificial neural network, we have 2 objectives. First, after the lecture, you will need to be able to lay down or lay out a math formulation for ANN and create pseudocode based on it. In the lecture, I will not show you guys how to do the pseudocode. Please do try it yourself. And if you cannot do it, go to your textbook. You will find a pseudocode there based on one example. And I will not show you guys how to do the coding, how to code a ANN, but if you're interested, come to talk to me. What we're going to do is that we will try to understand it, and then we will focus on the application of ANN in the lab. And you guys will need to play with different model parameters, the coefficients, and see how to optimize, how to get better results. So that's the first one, lay down a math formulation and create a pseudocode based on the math formulation. Second, you will need to be able to apply and modify ANNs to address problems, and we will look into that in the lab. First, in order to get a good understanding of ANN, because ANN is something that we create based on the working mechanisms of the biological neural networks. So biological NN, that's the original, the actual NN. ANN, that's an artificial thing. It's not a real thing. It's something that we create based on the mathematical model that we use to formulate the functions of the biological NNs. So let's first take a look at how we move from the biological NN to the ANN. As I've just mentioned, ANN, the artificial neural network, is inspired by the biological neural network. And when we are talking about this inspiration, I think we need to pay attention to two things so that we can better understanding the similarity and the difference. First is how, because we are talking about a network of neurons. That's the artificial neural network, the neural network. So for that one, in order to understand how the network works, first we need to understand how each unit cell, or in this case, how individual neurons work. And for this one, you will see that we will learn something called MB model. And then next, we need to understand how individual neurons can work together to form a network. And this one, that's what determines the architecture of the network. This one, in this lecture, we will see something. One is called perceptron. The other one is a multi-layer perceptron, MLP. There are some other architectures, but these days, these things, they are feed-forward neural networks. They are the most popular ones. Actually, they are predominant. First, let's take a look at the biological neuron networks. So you can see this figure. This figure in the middle here shows one neuron. And you can see that on the left side, we have this area. And this area, at the center of it, we have the nucleus. That's kind of the center, the brain of the whole neuron. And surrounding it, we have something called dendrites. Usually we have 5 to 7 of them for a typical brain neuron. And they have a tree-like structure. Each of them has a tree-like structure. And if we keep going, you can see that we have this. This is called axon. And as we keep going, moving to the next, to the dendrites of the next neuron, we have the tips of the axons. And the tips of the axons are in contact with the dendrites of the neighboring neuron. And there's small contact area, it's called a synapse. So this is the structure of a neuron, and its contact with neighboring neurons. What is really interesting is how individual neurons work. That is, so each neuron, they have their own electrical potential. And when the electrical potential exceeds a threshold value, then that neuron will be activated. And once activated, that neuron will send chemicals to the next neuron through synapse. And when the chemicals get into the neighboring neuron, those chemicals will change the electrical potentials of the neighboring neuron. So in that way, the neighboring neuron may be activated. So this process can occur from one point and then all the way propagate through the whole network, because each neuron is connected with several neighboring neurons. In summary, for biological neuron, so in a network of neurons, if a neuron is activated, then it transmits chemicals to its connected neurons to change their electrical potential. And when the electrical potential exceeds a threshold, neuron will be activated. Based on such an understanding, then we can create a mathematical formulation or a model Grab the process. And one of such models, the most famous one, is the MP model. MP is for McCulloch and Pitts. It's a pretty classic one. It's proposed in 1943. Now it has been widely adopted for ANNs. And in this model actually is just a mathematical description of the process that we just described. Simply, the model can be formulated in this way. Y, that's the output of a model. It's the function, active function of something inside it. So you can see that there are actually three components in it. First, we want to get a weighted sum of all the signals from the previous neurons. So we have this, and this is summation, or in some literature it's called a transfer. Second, we need to have a threshold value to determine whether the neuron is activated. And the third one is the activation function. And if we want to describe this using a figure, it will look like this. You can find this in your textbook. Let's say that we have neuron K. Usually, we have different layers of neurons. Within each layer, we have multiple neurons. We number all of them from number 1 to number capital letter K. And for any neuron from that layer, we call it neuron small letter k. Within it, we have a summation operator, and we have a activation function. After we finish activation, we usually want to add in a threshold to determine when the neuron be activated. And for inputs, we have multiple inputs. Let's say that usually we feed one sample. We can feed one sample or a set of samples into a network. Let's say that in this case, we're dealing with one sample only. One sample, sample I. We know that sample I will have different attributes. So I1, Xi2, all the way to Xij, capital letter J. That's why you have this J in the summation sign. And we have, for each attribute, we have a weight, just like what we did in linear models. But now it's a little bit more complicated since we have different neurons. So we have W1K, W2K, to JK. And K is the neuron, and it has J weights. So J weights correspond to the J attributes of the input sample. With all of them, we get a summation, then we compare it against the threshold. Then based on that difference of that comparison, we put them into the activation function. We can get what we need for the output. So if we have one sample, let's say output is a scalar. In this case, it's just yi. Again, you can see that three key things. First, it's the sum of the transfer step. Second, it's the threshold. And third is the activation. The summation is easy to understand. It's similar to what we did in linear models. So here we will not spend time on it. For threshold, we also had similar things before, just like the intersect we had in linear models. And previously we said that it can be viewed as part of the general parameters, right? We did that before. It can be viewed as part of general W, or a special thing is that it also can be treated as a special node. So there are two ways of dealing with the threshold. Activation is something that we want to spend more time next. The best activation function, or in theory, that we can have is a stepwise function. That's when the threshold value reach a specific value, when the value that we want to compare with the specific value reach that threshold, then we say that it goes to 1. If it's not reached, then it's 0. That's a stepwise. It jumps on all of a sudden. However, that type of function is not good for mathematical operations. For example, if you want to get a derivative of it, you cannot get it, right? Because go operate. Because of that, we usually use functions that can approximate a stepwise function. Two classic choices are the sigmoid, that's the logistic function that we played before. The other one is a new one, that's the hyperbolic tangent or tenth function. First, let's take a look at sigmoid or logistic. We learned this in the previous lecture when we were learning the logistic regression. This is the function of it. And you will see that later on when we want to do the optimization, we want to go have the forward pass and backward pass. One thing we will need to do, get the gradient or the derivative. One advantage of using this sigmoid function is that the derivative of it is very simple. You can try it yourself. Actually, you can derive it. The derivative of y is the function of it itself. So if you know the value of y, you can get the derivative of it very easily. Again, this sigmoid functions look like this. It goes from 0 to 1. The second one is hyperbolic tangent function. It looks similar to the sigmoid function in some way. Both of them are composed of that e to the power of x or e to the power of minus x. And for this function, the derivative of it is can also be written as a function of it itself, but it's different. It's 1 minus 1 y squared. The hyperbolic tangent function looks like this. It goes from minus 1 to 1. So last time when we were introducing the sigmoid function for logistic regression, we said that one purpose of using this, we want to squeeze or squash the input into a small range for the output. Here you can see that the ranges for these two functions are different. One from 0 to 1, and then for the new one, the hyperbolic tangent function, it goes from minus 1 to 1. This is significant because, for example, if you want to do a regression problem, you know that if you use the hyperbolic tangent function as the activation function for the last layer, then you know that your neural network only output values between minus 1 and 1. And if you use such a ANN for a regression problem, then you want to make sure that your labels, they are continuous. They should also have values between minus 1 and 1. Otherwise, you will get problems. And this is the activation. As I said, first we want to figure out how individual neurons work. Next, we want to see how to group neurons together to form a network. For that one, we are talking about ANN architecture. So ANN can have different architectures. In the early days, they can be very much diversified. You can actually design your own architecture for an ANN. For example, you can make it like something like this. You have different neurons and you design your own ways to connect different neurons. They can be pretty complicated. But after a while, people find that it's better or it's simpler to deal with neural networks with different layers instead of arrange things randomly. And there's one type of neural network called fully connected. That means for any neuron from one layer, it will be connected to all the neurons at the next layer. For the first one, like the second one is also like this. So they're fully connected. And then any neuron from one layer will not be connected to neurons in the same layer. So sometimes you see something called FC, that means fully connected. That's the architecture. And also, at the very beginning, it's hard to deal with multiple layers. So at the very beginning, people try to deal with neural networks, fully connected neural networks with only 2 layers. That's a classic architecture called a perceptron. Perceptron only have 2 layers, and one layer is an input layer. The other layer is a layer of function neurons. Here we call it function neurons because we have some mathematical operations associated with it. And for the input layer, in this case, there's no complicated operations. We just assign a value to it and then move the value to the next layer. In many cases, we don't count such an input layer as an independent layer. But in perceptron, it is still counted as one independent layer. And because it only has one layer of functional neurons, it can only deal with linear problems. It does not have nonlinear capacity. For example, if you have a nonlinear curve fitting problem, points, they're distributed along a curve. In that case, you will not be able to find a neural network that can perfectly separate the 2 clusters of points. Then we have the multi-layer perceptron or MLP. So in theory, This can also include those fully connected deep neural networks. But in this lecture, let's only talk about the shallow networks with only 3 layers. And another word that you will see is called feed forward. Feed forward, that means when we are thinking about the data flow direction, it will go only from one side to the other side. It will not go backward. So you will talk about connections. So these connections, you can view them as directions. They will only go along one direction. They will not go backward. But in more complicated architectures, you will see that we possibly have connections that can go across layers, that can go backward. And for this one, feed forward. There's no backward. Further connected, it will not go across layers. Third, talk a little bit about training. As I said, for any machine learning models, basically we need to think about 2 questions. First is how to create the model. That's how to do the training. Then how to apply the model. That's how to do the predictions. And for the training of new ANN, you will hear one word a lot. That's called back propagation. So how do you understand it? Back propagation. The simple way to understand it, you can think about this. If you have a machine in front of you, you can control it. You have different knobs, you have different buttons, and you do one thing, and for example, it will shoot something out to target. Then you will observe where that bullet, for example, end at, right? You compare it with the center of the target. Oh, you observe a difference. Next time, you will know that, possibly I just overdid it, right? So I should do it more gently. So your own brain, you have your own neurons, you know that next time I'll do it more gently. It's kind of, you adjust the weights in the neurons. So based on the difference between the current score and the center of the target, you get a difference. Based on difference, you generate a loss function. You know that, that's pretty far apart. So that's a bad one. So I need to adjust my weights so that they can go closer. Next time you do it very gently, you will find out, your bullets, this time is still far from the center of the target. And this time you did it too gently, right? So you need to adjust your weights again. I need to try a little bit harder, at least harder than this time, but it's more gently than the first time, right? You do it the next time. Third time you will say that, this time is closer. It's better than the first 2 tries, but it's still too gently. Then you need to try it even more harder, right? You keep doing this, eventually you will know the perfect way. That's actually how we train the neural network. You do one prediction, try it first, then you observe to see the difference. Or next time you want to adjust. The way to adjust is to see how big the difference is. And based on difference, you try to learn something. That's too gently, or you get it down too hard. And then based on that, adjust your own weights. So here we do it in the same thing. You go prediction forward, and then you go backward to adjust based on the observation to adjust your own model parameters. That's the backward process. And whole forward and the backward, the forward pass and the backward pass, that they form one iteration. Then you have multiple iterations, and your model will become better and better. And that is the back propagation process. In the broad sense. In the narrow sense, many people may say that a back propagation may only refer to the backward pass. But here in this course, when we say back propagation, we mean both the forward and the backward pass. And for the forward, we just need to do the prediction, right? We also talked about this in the previous machine learning models. For decision tree, I show you guys when you give one model how to use it to determine which classification that a model belongs to. That's the prediction process. Here's the same thing. For the forward pass, you just need to do it layer by layer, all the way from the input layer to the output layer. Usually you have one input layer, you have output layer. You have 1 to multiple hidden layers between the input and output layers. And we are talking about a 3-layer perceptron, multi-layers perceptron. Actually, we only have 1 input layer, 1 hidden layer, 1 output layer, right? But in the general case, when you do the layer by layer, for each layer, let's call it layer N. For layer N, let's say that we have input X and output of this, we're talking about only 1 layer, that's YN. Next layer, Let's call it n plus 1. It's the same thing. In this case, we will need to have its input, right? That's input x n plus 1. And usually the input of the current layer is the output of the previous layer. So this is the relationship. And we do it layer by layer because the input of the first layer, the input layer is given. That's the input of the whole network. And output of the whole network is not given, but we know the true value of it. And to do it, we just need to go back to the equation of the neural network. That's the MP model, because we know how to manage the operations for one neuron. That's here. And we stand it a little bit and write it in a tensor form. It's like this. The output of one layer, layer n, equals activation function. Inside the function, we have x, the input. Here, we put a bar above it. Let's say that it can be usually second order tensor. For the model for layer n, we have a dot product between this one and w. It's also, one whole layer is not a vector anymore. It's also a second order tensor minus theta. Theta, for one neuron, we have one theta, one threshold. But when from one layer of neuron, we would have a vector, usually it's a row vector of neurons. Here's n plus 1. So this is the forward one. For backward, as we said, the key is that we need to compare the prediction and the predicted and actual labels. Let's give out a very simple 3-layer neural network like this. It's a fully connected one. So every neuron in one layer will be connected to the neurons, every neuron in the next layer. At the end, we will get one prediction. Here we use this tilde to mean that this is the prediction. And we know the true label is y or y bar. Let's here use y. Then the loss function, we want to see how good or how bad this prediction is. Typical loss function is something like this. This was one sample. If you have multiple samples, then you just get a summation of it. So for such a loss function, we want to see how we can update the weight based on it. The way of doing it is like this. It's something called gradient descent. So let's say that you will take a look at one weight for one neuron, J here. We want to see how to update it. The way is that we know the value of this weight in the current step. And we just add a small change of it to it so that we can get the value for the new step. Now the question, how to get this W, the change of this weight. How to make sure that the change of this weight will give us better loss or a lower loss in the next step. That is the gradient descent. So we can think about a loss function as landscape. We try to minimize it, right? So we want to go to lower positions. Let's say that if you are standing on a mountain, and you want to go to the lower position, you want to go to the valley, right? You want to go to the valley, how to do that? The best way, of course, is you know the landscape of the whole area. You know how to go there. You do the planning directly. But in most cases, when we are doing optimization, when we're solving an optimization problem, we try to reach the valley, the lowest point. You don't have a map. We can only see small area surrounding us. We cannot see any further. So in that case, how to make sure that we can reach the valley, how we can go lower, how to do that. The easiest way, of course, we try all the directions surrounding us, right? We see which direction will go downward and have a very steep slope, right? And we find, oh, this is the downhill direction. Step in this way, make a step, you do the same thing again. See which direction you have is go downward and have the steepest slope. Oh, so that's the direction. Keep going that. You keep doing this, eventually you will go to a valley, right? That's how we do it. But what is the steepest downward direction? How to do that? If we are talking about this mathematically, actually we are trying to get something called a gradient. For example, if you have a function f or y as the function of several coordinates, x, for example, y is a function of x, how to do that? Then that direction can be obtained if you get a derivative of y with respect to x. But if you have function f as the function of x, y, z, then you need to get a derivative of f with respect to x, with respect to y, and with respect to z. Because now it's really a problem. So you need to get three things. The three things give you the projections of one vector on three axes. Just like velocity, you need to know two things or three things, components, so you know the direction of it, right? Here, the gradient is the same thing. So depending on how many dependent variables that you have. But the key thing is that we need to get a derivative, or in a more general case, we need to get the gradient. And the gradient actually will give you the direction that it will increase in the fastest way, not decrease. So the way to reduce the function fastest will be the negative of the gradient. For example, if we are at one point here, we can draw a contour. We want to go uphill in the fastest way. We will need to go along the direction of this. This is the gradient of L. This sign is called Anomaly L. That means the gradient of L. And to say that now we want to reduce the objective function or the loss function, then we need to go along the negative of this gradient. So it's going to be minus delta L. Sorry, not delta, Anomaly L. And this and we know that this is go lower. You want to go lower, we need to make sure that we have something called a gradient descent. And now we have another problem. Now we know which direction to go. We still need to determine how big a step that we will make, right? For every step. You know the direction to go, you need to show go this way or make a bigger step, right? Something we call learning rate. We use one parameter to do it. So for this change of weight, we said that how can we change weight? What we do in the gradient descent method is we said that the change in the weights should be proportional to the gradient. Actually, it should be along the negative of the gradient direction. So we have a negative sign here. Sorry, this is not a minus. So eventually we have something like this. Because this gradient is the derivative of the object function with respect to this coefficient or this weight. And this eta, or in some literature, people use alpha, means learning rate. This learning rate is a hyperparameter. Nobody knows, what is the perfect rate. There's no mathematical equation for it. There's no analytical solution. Many cases, you need to try. Or many cases, the values for the learning are based on experience. But usually we need to start with a small value, less than 1, like 0.1, 0.001, and then keep reducing that learning rate. Because we know that at the very beginning, you can keep just make big steps. And when you approach the bottom of the value, you need to make sure that you need to be cautious. Otherwise, you're going to miss some point. So that's why the learning rate usually need to be continuously reduced in the learning process. Okay, this is still like a general description of the process. Next, let's take a look how to do this step by step. We want to take a look at the detailed backward pass for a 3-layer network. We'll show how to get the gradient. And for this one, you can see that input layer is the lowest layer, and output one, that's the one on the top. And the hidden layer is between input and output in the middle. And for input layer, actually it's not a function layer here. You can see that what we do is that we just enter, if we are talking about one sample here, we have different attributes, x1, xj, all the way to x capital letter J. We just give these different attribute values to different input neuron. And the input neuron then enter the values to the next layer. In that process, you can see we have the weights for the hidden layer. We use the symbol VL1. L, here's the neuron number. We just use one neuron as one example. This is this neuron. You can see that when the hidden layer, we have neuron 1 all the way to neuron capital letter L. We just use one smaller L neuron as an example. For this one, it has J, sorry, there's one problem here, so it should be capital letter J. We have J weights corresponding to the J input neurons. Those V, these weights, they just be used as the weights for the summation, the weighted summation. So it's here. You can see that is the first step. We have V as the weights. We get the weighted sum of them. Then we will get this alpha L. So we combine all these things into one value here. Alpha L, then we'll have a subtraction operation. Will be compared with this gamma L. Gamma L is the threshold. It will be compared with threshold before it enters the, here's the activation function. And then after we apply the activation function to the difference between alpha L and gamma, we'll get output of this neuron. It's called BL. So that is here. We do the summation, we get alpha, then we apply this activation function. Here's we try to compare alpha L and the threshold, and then the difference will be used as the input for this activation function. We will get output BL. Next, we go to the next layer. Now we get the output of the hidden layer. That's the B. For example, for this neuron L, we get a BL. All right, for the next layer, we will have the same process. Very similar. But now we use different parameters for it. First, we need to get something very similar to alpha. That's the weighted sum. So here we call it beta. For example, the beta for this K. We just use this K neuron output layer as an example. For K, B, beta K, just like the alpha L, is the weighted sum of all input from the previous layer, right? You have all these things connected here. And for each of them, we have a corresponding weight. So you get this. It's a weighted sum of the B, the output from the previous layer. So we get a beta K. Beta K will be compared with this theta. That's the threshold of the output layer. We get the difference between these two things, put them into the activation function, and we will get YK. That's output. A 3-layer neural network, you can see that the job is already done, right? You get the YK, that's actually your prediction. We usually use this tilde sign on top of it to represent that as a prediction. So it's not too complicated, just 3 layers. The first layer is not a function layer, so it will not take any effect. It just assign the values to it. Then for the next, the hidden layer and output layer, you will see that we will have these mathematical operations. 3 things: summation, then the difference for the comparison, then activation function, right? So this is the forward pass. And we said that what is difficult is not understand how to do the forward pass. The difficulty is how to come up the equations for doing the backward pass for the training. To do that, first, we said that everything is done based on an estimate of something that we do, right? You assign some random values to the model parameters, to the weights. Then you, based on the model, you make one prediction. Then you compare the prediction with the true label. You will get the loss. We want to estimate which direction to go based on the loss. So the first step is to give out the loss function. Loss function is actually introduced this before. Here for the last layer, we have K neurons. We need to sum up the errors caused by all the neurons. YK, we can switch their positions. YK tilde and YK does not matter because we have a square here. And if you want to write it as the tensor form, it's going to be like this. We also learned similar things in SVM. Next, because we need to get the weight, right? We need to get this delta something. And let's take a look at one specific weight, KL. That's the weight here, right? That's the weight, this line connecting this neuron in the hidden layer and the K neuron in the output layer, right? That's this one. For this connection, there's a weight to KL. We have many different connection lines that corresponding to different weights. But for this one, let's use it as one example, see how to do it. We know that based on that gradient descent method, it will be the negative earning rate eta times the derivative of the loss function with respect to KL, right? That's the method. Then how, this is something we don't deal with it. We don't want to derive the function. We don't know how to calculate it. In order to calculate it, we need to derive an equation that we can use for calculation. So do it. You can take a look. L here is on top, is here, right? L is a function of yk, right? And yk is a function of beta k. So here is also the same thing. And beta k is a function of kl. And when we are doing derivatives or gradients, we have something called a chain rule, right? If, for example, if we want to get a derivative of with respect to x, if f is also a function of y, then we can do is that we can try to get the derivative of f with respect to y, then get a derivative of y with respect to x. Then the product of these two things will be the derivative of f with respect to x. That's what you learn in calculus. So here's the same thing. You can see that we want to get the derivative of L with respect to WL because they're not directly connected. We have some functions between them. So we can do it step by step. L is a function of yk tilde, right? And this yk tilde is a function of beta. So we get a function of yk tilde with respect to beta k. So please pay attention to this. This is kind of the key thing. We need to understand how you do the backward pass. And then beta is a function of what? KL, right? That's what we want. So then beta k to partial WKL. So now you can see that this is the chain rule. Let's take a look at these things separately. So first, try to do it. Can you let me write down this minus first. How to get a derivative, partial derivative L with respect to y tilde. You have the function here, right? Or here. Can you do it? There's a 1/2 here. Just copy it down. And this is the second power. The derivative of second power will become 2 times it, right? Then 2 times yk tilde minus yk. Then it's done. Next, let's take a look at the derivative of yk tilde with respect to beta k. Here is here. Yk tilde is a function of f beta k. So the key thing is the activation function, right? We need to get the derivative of the activation function. That is what we learned when we are introducing the activation functions. Depending on which function we want to use. For example, if we are talking about the logistic one or the sigmoid. Sigmoid, the derivative of it is y times 1 minus 1, right? Here, because the y is yk tilde. So if we use a logistic sigmoid function as the activation function, then the derivative of it will be yk tilde times 1 minus yk tilde. Then second part is done. Next, I want you guys to try one thing yourself. It's actually simpler than this one. Please, let me finish one thing before you do that. Usually, it's simple to do one thing. Here's this equation looks pretty complicated. Later on, as we keep going, now we start talking about the output layer because we go backwards. So the output layer is the first layer that we will need to deal with. As we keep moving on, the first one hidden later, we will see this thing will possibly become longer and longer. So we want to simplify it. And for instance, for shallow neural networks, and if you go deeper, you will have more than 3 layers and more than 2 function layers. In that case, this equation will be really hard. So we want to do things recursively by finding the pattern when we move from one layer to the other layer. We will talk about the pattern here, but now let's first to do a simplification. We will do this. We will take a look at this term and we will do the simplification. We call this one gk, and then g sub k equals just is the first term and the second term. So it's partial L, partial yk tilde times partial yk tilde, partial beta k, or is also partial L, partial beta k. That's gk. So gk equals this. And because of that, now we can simplify this delta L. Delta KL will be the increment in WKL that we need to add to it. So we can modify the coefficient. If you take a look now, equals minus, we still have this eta, and all the things from here to here now becomes GK, and we still have this BL thing. So now you can see that it looks pretty simple, right? Alright, now I want you guys to try one thing yourself. Please try to derive this theta k. Please do it. I will give you guys 2 minutes. Again, theta KL, we are still talking about the gradient descent. So we still have eta. The change of any parameter is proportional to the derivative of the loss function partial L with respect to the parameter itself. So here should be partial theta KL. Then take a look to see how to move from L to theta. So we can figure out how to use that chain rule. We take here, L is a function of yk, yk is a function of theta. So there's only one intermediate variable between theta and L. So instead of doing it directly, we now split one term into two terms. So we can include that intermediate variable into the chain rule implementation. So it's partial L, and intermediate variable here is just partial yk tilde. Then we have yk, because these two things should always be the same. That's the chain rule. And yk tilde is a function of theta k, so it's partial theta k. Next, just write down these two equations. Partial L, partial yk. We did this. If you don't know how to do it, just do it yourself. It's calculus. You know the function of this thing. You want to get derivative of it. And it was just partial eta. We also did this in the previous step. So this is the first term. And this is the second term. So first term, we just copied down. The 1/2 and 2 will be canceled out. So we only have 1k tilde 1k. That is partial L, partial yk tilde. That's the first term. Second term, partial yk del tilde, partial theta yk tilde times 1 minus yk. You can see it's the same thing as the first one. The only difference is that now there's a negative sign here. Negative sign in front of theta k. So we should also have a negative sign here. There are two negative signs, so the two negative signs will be canceled out. And eventually we will get eta yk tilde minus yk times yk tilde times 1 minus yk. And if you compare it with the first one, we made a simplification. We said that here to here all equals to gk. So we should have eta gk. Because we don't want to deal with long equations, so we define this big part in the equation as gk. That's it. So you can see that it's not complicated. Do it yourself. That's for the first layer. Next, for the hidden layer. Now things will become slightly more complicated, but it's not as challenging as you think it would be. It just needs a little bit more attention because now we need to do more. So in the first layer, we have the model parameters, theta and beta, right? So what parameters we have for the hidden layer? The first one, the weight actually is W. So second one, the weight is theta, right? Theta and gamma. These are the things we want to update. You can see first one, we updated theta and W and theta for the first one. Second one, we want to update V and gamma. So first, let's take a look at V. V is similar to the W in the first one, in the hidden layer. We want to see what change we should have for V, Lj, and based on that gradient descent, we should have this, right? It's proportional to the change of the derivative of the loss function with respect to these parameters. So it should be partial VLJ. Next, just take a look how to move from L to VLJ. Oh, that seems to be a long path, right? That's going to be a long chain. What should we have? We need to go from L to V. So which chain we should have? We should go from here to here because backwards, so we go from top to the bottom. L is a function of what? Yk tilde, right? That's first node. Then yk tilde is a function of what? Is because here's B, so it should be B, right? Then B is a function of something should be alpha, right? And alpha is a function of V. So that's the chain. Then we need to follow the chain partial L, partial. That's a long chain, but let's make one simplification. Because in the first step, we made a simplification. We say that gk equals partial L, partial beta k, right? It's like short part of the long chain. So it's yk, beta k. There's something between them, but I would make simplification. So let's make a simplification. We jump from L to beta k directly because we've already defined it in the first step. Then partial beta k is a function of BL, and BL is a function of alpha L, and alpha L is a function of what we are interested. That is V sub Lj. Here we go. Now it's done. Next, just do it step by step. First, oh sorry, I forgot one thing. Don't forget this. minus 1 eta. Make sure you write eta in the correct way. It's like this. See how you write it? Just like this. So we should have minus eta here. First, the beta, partial L, partial beta K, we've already defined it in the first step. That's GK. Second, partial beta K, partial BL. What should we have? What's the coefficient in front of BL? KL, right? So the derivative of beta K with respect to BL just would be the coefficient in front of it. For example, you have a function y equals 2x. Then you want to get a y prime or derivative of y with respect to x. Then just would be equal to 2. So we have WKL. Next, we want to get a partial BL, partial alpha L. Interesting. Now we hit another activation function, right? Depending on what we have, sigmoid, the derivative of it just would be the function times 1 minus the function. Here's the function's BL, so we should have B times 1 minus BL, right? So let's mark it. 1, 2, 3, 4. And here, 1, 2, and 3. Last one, partial alpha L, partial VLJ. What should we have? XJ, right? Just take a look at the coefficient in front of it. So it's XJ. Now it's down. But the problem is that, this is still look pretty long. We want to make a simplification. Here we usually do it in this way. We group all the terms 1 to 3, and we call this one E sub L. Then the whole thing will be simplified into minus eta ELXJ. And again, EL here equals the products of the first 3 terms. So it's from here to here, that equals sub L. This is the new term, the quantity that we just defined. The purpose to make things look simpler. And then for delta gamma L, the threshold, we also need to figure out how to update it. Here, I don't want to show you guys how to do it again. It's very similar to what we did in the first step. They're very similar. This actually, the change in the threshold is simpler than the change in a regular neuron weight. The only difference is that if you take a look at the first one, you can see that they're very similar. The only difference is that first the sign is changed from negative to positive. Second, we don't have this last term anymore. So here we would have the same thing. We equal to first the sign change from positive to negative. Then we have write down GK, WKL, BL times 1 minus BL, and that just equals the E sub L. So that is how to do a backward pass for a 3-layer perceptron. You can see that it's not difficult. Now with such information, you should be able to develop your own code for implement a shallow neural network. Here I want to put down a note here. That is when the activation function is switched from sigmoid, again that's the logistic thing that we did before, to hyperbolic tangent. Quantity 1 minus yk theta will become 1 minus yk theta. If you change the sigmoid function, we learned this. Another term that's relevant to the derivative of the function is BL times 1 minus BL. That will also become 1 minus BL squared. That is the backward pass. But here I want to do 2 more things. First, you can see that everything is written using the index notation. You have all the subscripts that look pretty complicated. When you try to implement this, you'll find that we still need to deal with arrays, right? With the shape of array, how to arrange all the data. That is hard to see from the subscripts. So we want to convert everything to that array notation that we did in the previous lectures. That's one thing that we want to do. Second thing, we want to find the pattern to go from one layer to another layer so that we can generalize this process from a 3-layer perceptron to neural networks with more layers. Let's do this in the next section. The general backward pass for 3+ layers. Again, we are trying to do 2 more things. First is to get array notation. Second, we want to find the pattern to write everything in a general way, so that if you code your network with 3 more layers, then you know how to do it. In the above deduction for the 3 layers, you can see that it's pretty complicated because we use different things for the same weight for different layers. We use W for the output layer. We use V for the hidden layer. That makes things look pretty complicated. Now we want to simplify So we will do it in this way instead of dealing with different variables. So we want to do a generalization. That is for every layer, as we mentioned before. We have the output from the first layer. Let's call the first layer n, and the current layer n plus 1. We want to figure it out. We know something from n, that's the output. Here we call it vector O. How do you move from this vector O, that's output from the previous layer, to the next layer, n plus 1. And we know that the first thing we need to do from the top, we need to do the summation thing first. After summation, we will get one thing. Here, we get a summation based on all the weights. We will get alpha. That's for the hidden layer. Here, we do the summation with the weight W. We get a beta. So for the alpha, beta, let's call them I, or generalized I input, the input for the layer. So I, next, what we will do is that we will, for this I is just a general term for alpha and beta. We want to add in the threshold. So we add in the threshold here, compared with the threshold. Let's call it, it's also a vector. We use a superscript to tell which layer we are playing with, and subscript for neural numbers and layer numbers. Here we can have the activation function f, and after activation, we will get the output of that layer, theta n. Next, we go to the next layer, and next layer we have this again. So you can see that how we do it. Sorry, this is n plus 1. This should also be n plus 1, my bad, because we are in layer n plus 1. So based on this, we try to generalize everything using a new simple system. So first, let's take a look at the last layer, because we're doing things backward. We go from the last layer, output layer, to the first layer. But output layer, we don't need to do everything again. Just take a look at what we got. Is that we have this one key equation is this one, second one key equation is this one, right? So just copy it down. W data. Now we want to write everything using the array notation. W here should be a tensor, and because the last layer, so should be a capital letter N. Equals minus eta. Here in the original equation we have GK times BL. And if you read that one subsection in the first chapter of the textbook, you will find that this actually is just a tensor product between two vectors. GK is a vector, BL is not a vector. When you have one subscript, well, that means that array have one dimension, is a vector. So now we are using array notation, so where you need to carry, so every vectors and scalars need to carry a vector sign or a bar. And this is n times O n minus 1. So that's the output of the previous layer. That's how we get it here. It's the same thing. B here, B is the output of one layer, so here we generalize it, we use O. And for data, so theta n, we do it in the same way. It's similar to the first one. The only difference is that there's no O anymore, and we need to switch the sign. That's it. We did this. Now we just convert everything from the subscripts, the index notation, to array notation. And there's one more thing, that is Gn. That is the thing that we need to pay attention to, because Gn is also a vector here. Equation for Gn is here. It's yk tilde minus yk, this the whole thing. So now we want to write everything using using a array notation. So it should be yk tilde, it is a vector, so we put a vector sign above it, minus yk y, so it should y vector y. Thing between them here, everything is k. So it's actually, this is an element-wise product. Element-wise product is just this. And here yk tilde. So you can see that we don't play with subscripts anymore, but now we need to carry all the vector and tensor signs, and we need to pay attention all the product between different things, because now we're not dealing with terms. We're dealing with a vector containing all the terms, all the components. That's it. That's the last layer. We want to do the last layer because the last layer take the input from the yk, that's the output of the whole network. And when you move to the next layer, you need to take the input that does not deal with y anymore. So all layers, their operations were slightly different from the first layer. Other layers, there's going to be a difference for y, vector y. Now we use smaller n. That means any other layers, because the gain is partial L, partial I, vector in. This is what happened for the last letter, this one. Now we don't have this, but we have something else. You can derive it yourself. Here we will skip the deduction, go to the conclusion directly. All the other things, they are very similar. But now we don't have y anymore because we only have output. And for, sorry, w should be a bar, not a vector. This one, it's the same thing as the previous letter. But now it's not capital letter N anymore because capital letter N is for the last letter. Small letter n is for anything between 1 and a capital letter N. It's the same. Just switch from N, capital letter N to smaller n. Same as the previous letter, the only difference is the treatment to G. Because here G need to take the Y, that's output of the last letter. Now we don't have that. Instead, we have the output O. So that is what we need to know about shallow artificial neural networks.
I think I'm falling for you.